Welcome to another Space Startup News Live. I do this live stream every week at the same time, and I recap my videos I've done this week. Typically, I do 2 videos on dedicated subjects, and then I do a space news video, and I finish the week up with a live stream. So I think this is the 25th one I've done so far. So if you're watching, thank you for joining, and chat from Marty the Martian. Good morning, everyone from down under. Welcome for joining, Marty. So let's begin with the very first video I did this week, which is on Cislunar Industries, which they are working on metal foundries in space and on the moon. So I came across this company through the Lunar 10 DARPA study, which was, I think, 13 or 14 companies that were all proposing to DARPA commercial services they could offer on the moon. And Cislunar Industries did a study on a lunar foundry. And you can see from the actual graphic I put on the thumbnail that they take into the foundry ISRU metals. That's metals that have been produced from the lunar regolith. They can take in scrap metal or slag. They can also take in like defunct landers or rovers or metals from science experiments or whatever that have completed. Whatever, you put it into the furnace and you can get out ingots, rail tracks, beams, sheet metal, extruded profiles, cables, wires, additive manufacturing, even mining equipment. And in the DARPA study, they have a few slides, and you can see here the yellow bits is what they can produce from the foundry. So you can see rail tracks and all kinds of support equipment. They can produce all the metal bits on rovers, some kind of compactor, crane. These are kind of like weights to put on some kind of excavation equipment that holds down the equipment and means it has more traction, which means you can dig into the regolith. And you've got for front loaders, you've got the front bit of it. So there's lots of different things you can produce from a metal foundry. And so this is the one of the slides from their study. So they propose, first of all, and this is from a NASA study, they propose also what they call a modular space foundry. So foundry that they have in space, it's in orbit, and they got funding for phase 1 and phase 2 from NASA. SBIR means small business, it's a small business grant. And so basically there's a lot of metal floating around in space. It's mostly aluminium from upper stage rockets and satellites that have stopped working. It's actually, when you add it all up, it's thousands of tons of metal just floating there, which is kind of just in the way. It's debris, it's dangerous, but it can stay up there for decades, even centuries, depending on the orbit. So the idea is Cislunar foundries. I actually got a graphic, kind of explains it a bit more, but Cislunar Industries will have a foundry, and other companies, say Astroscale, can pick up the upper stages, send them to the foundry. The foundry can then basically melt them down and produce whatever, ingots, metal rods, or whatever metal equipment you need, and then they can be used for in space. I do mention there's at least 2 companies working on metal propellant drives. One of those companies I knew about, MagDrive, because I've done a video on them. But there's another company called, I think, Newman Space, which I think is an Australian company. Maybe I'll do a video on them at some point. But basically, Cislunar Industries is working with Newman Space to produce metal propellant drives. And all it is just a rod of metal. I think there's a gap in the middle. But that is basically put into the drive, and it uses an electron discharge arc to vaporize the end of the rod, and then the plasma is then accelerated out at the back, and that produces thrust. So metal foundries in space can be used to clean up junk to produce metal propellant drive rods or other equipment. I also mentioned trusses for solar power satellites. Those would actually be hundreds of meters or even kilometers in length. And so the metal foundry can just generate a large truss that you can use to put the solar panels on. Or for communication arrays, there's like lots of uses, right? Once you start producing metal in space, there's lots of potential uses. And Wayne's World of Science and Technology saying, good evening. Thank you for joining, Wayne. So yes, we're talking about metal foundries in space and potentially on the surface of the moon. So this is, I think, the first page from their DARPA study, and it's called Metal Extraction, Treatment, Assembly. And they're talking here about prospecting for potential sites to harvest regolith on the moon, mining, processing, refinement, which is metal separation, space foundry, so logistics, and use cell. So basically, this is a proposal they made to DARPA. And this is another slide. So you can see it's using mine site, primary sizing plant, mining equipment. So it's using Gitai, which is one of the other companies involved in the DARPA proposal. I think that's a Japanese company that produces mining equipment. Then you've got the ISRU production. They're talking about importing scrap, metal, and deoxygenated regolith. So a lot of the space startup companies want to extract oxygen from the regolith. The reason they want to separate oxygen is they can sell it as propellant. Well, it's the oxidizer. So Blue Origin and also SpaceX Starship both require oxygen as the oxidizer. In the case of Starship, it needs about 1,000 tons per Starship. The Blue Origin Mark II lunar lander is reusable. So if you produce oxygen on the moon, you can sell it to Blue Origin, to SpaceX. Oxygen can be used for life support. It can be used in fuel cells. Combined with hydrogen, it's water. You can use it for irrigation, for plants. So you can make a business plan for producing oxygen. So the byproduct of that is deoxygenated regolith. So that is perfect feedstock for a foundry because it's metal rich and you've already removed the oxygen. So here you have the deoxygenated regolith. You have metals from landers or whatever, and that goes into the foundry, and you get out all kinds of stuff. Talk about trusses here. You've got wires, rail tracks for Northrop Grumman's proposed lunar rail network, sheet metal, and of course metals can be used for construction, for habitats or warehouses or masts. So that's their proposal, and I think I showed these before. Potential products are wheels, tracks, crane structures, mass blocks, counterweights, digging teeth, buckets, blades, compactor rollers, and customers would be customers working on construction projects on the moon, mining, ISRU for the mining equipment, and logistics, which is the rail track. Presumably that's what they mean. And here, what did they say? Products are rails, fastening hardware, which is that fastens the rails to the sleeper beds, and rail track components, wheels, frames, panels, bridges, of course, bridges to go over the craters, so you don't have to go around corners. In my rail network video, I say it's really difficult to go around, to curve around corners on the moon. So you basically want to do bridges over craters. So metal would be very useful there. And also additive manufacturing feedstock. So you can create spanners and hammers and nails and all kinds of stuff using additive manufacturing. So that's their proposal. Let's see if yes. And they're working with a lot of other partners who are also part of the DARPA study. Obviously NASA, the Artemis Space Camp, and the Commercial Lunar Payload Services Program. And Wayne's World is saying, you know about the planned launch from Newfoundland? Yes, that's Nord Space. I mentioned them on Wednesday in the midweek Space News Roundup. They had a problem with the fuel mix. I think it's a bit too fuel rich. But anyway, they weren't happy with the mix of the fuel and the oxidizer, and they can't really fix that at the launch site, so they have to go back to Ontario, produce a new batch of fuel, and then try again. And obviously, they're going to need a new launch license and so on. So maybe it's going to be a month or two before they're ready to try again. It's the very first launch, and it's expected it's going to take a while to figure out all the problems. I mean, right at the beginning, you're just going to have so many potential problems you never come up against before. So they'll figure it out. Maybe it'll be next month. I mean, how long did it take Gilmore Space to launch? A long, long time, right? So I'm sure Nord Space will figure it out soon enough. So Cislunar Industries is working with Share Space. It's working with Axiom Space, NanoRacks, which I think is owned by Redwire now, and Astroscale, obviously for finding the satellites and so on and sending them to the Metal Foundry. So yeah, they've got quite a few partners. Potentially they've got customers, and they've got funding from NASA. Phase 1, Phase 2 small business study, and they got funding from DARPA as well. So obviously a foundry in space would potentially be useful to a lot of startups, companies, NASA, the US government. So let's see what people are saying in the comments about metal foundries. So I'll just put myself in the corner here. So Wingsley is saying, wow, let's hope we all live to see some of these technologies and firms make an impact in space. Yep, I agree. So I think I mentioned in the video, they do have a flight coming up. I can't remember the details about the flight. They've already done the the zero G flights, and what else? Do I have any notes saying about the flight? I don't have any notes about the flight, but basically, I think they have a flight in 2026, and they continue to do the zero G testing. They've already managed to make metal ingots in the zero G flights, and one thing I mentioned in the video is that a single Starship, if you were to extract all the metal, or I think it's 80% of the metal, you can produce 10 kilometers of rail track from a single Starship. So, that's very promising. Joe Gogent is saying, back in the early to mid 2000s, I wouldn't have taken these projects seriously. However, now with the second space race kicking into high gear, it is nice to see the space ecosystem take shape. And that's another thing. This is part of ISAM, which is in-space assembly and manufacturing. That's now a growing sector. You've got a lot of companies involved in doing things in space. You've got all the space tugs from Impulse Space and Quantum Space. You've got the Orbit Fab for the refueling in space. You've got Astroscale for their remote proximity operation and docking. There's multiple companies involved in tracking a satellite, docking with it, capturing it. That could be for orbital debris removal, but once you've docked with it, you could then send it to the Metal Foundry in space. So you've got the solar power satellite companies, which are building things in space. You've got the commercial space stations. So there's a lot happening in space. And now you've got Metal Foundry, which is fantastic. And if I just get rid of myself for the moment, Martin the Martian saying, I've been waiting many years for this. Back in the early days of the shuttle program, it was suggested that the main fuel tanks to be boosted to a slightly higher orbit for in-space reuse. Instead, it was decided to just dump them all back into the atmosphere, losing many tons of usable mass. Now, at least, we may be able to make better use of space waste. Precisely. I remember those days when you saw the orange fuel tank, which was massive, and it was in space already. And you think, well, you could just seal it and make it into a habitat or something, or make it into scrap metal and reuse it. But no, they dumped it into the atmosphere. So hopefully, with a metal foundry in space, we can actually reuse the metal that's already there. And most upper stages are just aluminium. So you could use additive manufacturing to produce all kinds of equipment and trusses and whatever in space. So hopefully in the future, that's what will happen. So my second video I did this week, here it is, if I bring it up, is metal giant glass spheres for lunar living. And you can see from the graphic, there's a whole series of concentric spherical glass spheres, and in the center one, you outfit all the floors. There's a core elevator that goes through the center, and at the top you've got a platform for plants and trees and so on. And at the bottom is the actual thing that produces the glass. Basically, you collect lunar glass compounds, and then they're melted using a microwave oven, and then you can blow these spherical glass structures. Basically, you use argon gas, and it inflates the glass into a shape, into a spherical shape. I think I may have a video somewhere. When I find the video, I'll bring it up. But basically, here's a bigger image. What it looks like once it's outfitted. So there's multiple spheres here, and we'll get into why the spheres are like that, why there's many spheres. Some of the comments kind of have issues about glass and being impacted, and so we'll get into that later. But so what do I want to say about the glass spheres? Well, I want to say that here's another graphic here. So the way this works is, and there's a nice video that renders the whole mission by Nick Henning, and that's in the video. But basically, you land a I don't know how you can see here, right at the base. This is this piece of equipment that you put in the lunar glass materials. There's a microwave oven that heats them until it's liquid. Then there's a metal pipe that ascends with the molten glass, and then argon gas is injected into the glass material, and it expands into a sphere, like a balloon, except it's glass, and you get this almost perfect spherical shape. And you can do that multiple times to get these concentric glass spheres. And then you can see the inner one has regolith around it, and in between the spheres you have compressed argon gas, which is inert, doesn't react with anything. Oh, I don't know what happened there. And it helps thermal buffering. So you've got these wild temperature swings on the moon. It gets very, very cold, minus 170 degrees, and then it gets very, very hot, 120 degrees. And that's cycling every 2 weeks. So having these different spheres buffered with argon gas helps get rid of all of the swings in the temperatures. And yes, and I do mention in the video there's various proposals, over the last few decades on glass structures. So the lungs proposal that I'm talking about in the video is about 20 to 50 meters in diameter. And it can be a habitat for dozens of people. The Japanese lunar glass proposal is 200 meters and up to 10,000 people. That would be not one single piece of glass. It would probably be layered glass with metal support. And then you got the Lunar Dome vision from Ed McCullough, which is 40 kilometers, 25 miles. And that's obviously, that's a lot of metal with glass sheets. So that would be a very, very big project, city scale. But you can start small with a 20 to 50 meter diameter glass sphere as proposed in this lungs proposal. And you can see like a side view and a floor top view plan. So the side view on the left, you can see the elevator, the core elevator. Then you've got bridges, and at the end, at the side. You then have your walkways, you have your amenities, your workspaces, living quarters, and so on. And from the top view, you've got the elevated core, you've got a sky bridge, small plaza, and then you've got living working areas. And you have many floors. As you can see here, there's an internal graphic. So you've got the core elevator, and then you've got the sky bridges, and at the edges you've got all your work areas and so on. So it looks very nice. And here's another graphic. So you can see here at the base is the microwave oven that melts the glass. You've got solar panels, you've got your airlocks, you've got your rovers and so on. And then you've got internally, you've got all the different floors, and you've got the top deck with where you can see out, it's all glass, and you've got trees and so on. And here's another graphic, and you can see the concentric glass spheres, and then the inner living sphere called the nest with all your life support systems there. So before we get into the comments, I think I have a video here. Oh yeah, so here's the Nick Henning animation, which kind of explains a bit more how it works. So you land your oven, your microwave oven, on the moon, and this example is using a Starship vehicle. So here's the equipment that produces the glass spheres. So you put it on the surface. You then prospect for lunar glass compounds, and you can find those on the moon. They get put into the furnace. Got solar panels to generate the heat. So then you start heating up the lunar regolith. And you can see there it's very hot molten glass. Then a pipe pushes up the lunar glass, and then compressed argon is blown into the glass, and then that generates the sphere, which is of course very hot. Then it cools down, but you get this almost perfect spherical glass sphere, and then you can blow another one inside it, and then 2 or 3 or 4 or 5. And the reasons for that, like when we get into the comments, you'll understand like the reasons why you have multiple spherical spheres. And then in the inner one, that's where you'd fill it with air. You'd put regolith around the outside, core elevator, and then you outfit all the equipment and so on, and then you have a habitat. Yeah, so get rid of that now. So okay, let's get on to the comments, because there's quite a few comments on this. So let's bring them up. Put myself in the corner. So Regan Palman 5491 says, frankly, I think lava tubes are a better choice for habitation. They have immense advantages in radiation shielding and thermal stability. The only thing the glass domes have going for them on the moon is the availability of construction material and the convenience of putting them where you want them instead of where they naturally occur, as with lava tubes. However, I do see tremendous potential for these as L5 habitats. L5 is one of those balance points between the orbit of the Earth and the moon. There's L1, L2, L3, 4, L4, L5. And if you put something there, it kind of stays there. The station keeping is quite easy to do. So you could put large structures there. They generally just stay there. So yes, so that would be in space between the Earth and the moon. You could have one of these glass spheres. Everything you said about the 1/6 gravity environment of Luna is even more true in microgravity. And instead of platforms, paired counter-rotating rings could be built within. Put water between the outer and inner spheres and use it for aquaculture, as well as highly effective radiation shielding. So yeah, I mean, that's all true. Water is great for radiation shielding. Also, you need water for life support, aquaculture. Yeah, and of course, it would be even easier to make perfect spheres in space. There's practically no gravity, very minimal gravity, and yeah, you could have even bigger spheres in space. And I think there's a graphic from the actual company. It's gone now. But basically, on the website, you can see they have one of these sphere habitats in orbit. So yeah, you can have them in orbit. You can have them near Earth asteroids. You'd have all the materials needed. The only issue there, I think, would be the argon gas. And we have Vast CNC saying, wouldn't that irradiate the water? So I think the water would be enclosed, so it couldn't escape. But yeah, I mean, that's just an idea of you know, I mean, water as radiation shielding is not a new concept. There's quite a few spacecraft designs that have a lot of water, you know, to protect you against solar flares and so on. So back to the comments. User SZ5SLM is saying, a very dangerous project. Will a glass habitat on the moon withstand a meteor shower or moonquake? So let's have a look at this, because I anticipated this question. So this is what's called a Whipple shield, and they're very, very common on spacecraft. And you can see it's just a number of layers. You can see there's been an impactor here. So you have 1, 2, 3, 4, 5 layers. And you can see from the graphic that an impactor hits the first layer. It goes through the first layer, but it's lost a lot of kinetic energy. So by the time it gets to the second layer, maybe it goes through the second layer, but it's lose even more kinetic energy. And eventually, one of the layers, hopefully, completely stops the impactor. So that's the idea of Whipple shields. You have multiple layers, and they stop the impactor. And as you can see here with the design, you've got 1, 2, 3, like the fourth layer is the one that is where you have the crew, and you've got, this is a regolith layer as well. So this is kind of like a Whipple shield. You've got multiple glass spheres, and the outer one is expected to be to shatter or to crack when there's an impactor. That's expected, but it takes a lot of the kinetic energy from the impactor, and then you'd have a second and a third and finally a fourth. And I do mention in the video that if you network these glass spheres with tunnels, in the case of an impactor that gets all the way through, you could evacuate to the tunnels, which would be pressurized and airtight, and you could even have a storm shelter in there as well. So you'd have these multiple spheres, all with tunnels, all connected together. And another thing you could have around the spheres, you could have metal barriers, nets made of woven metal that would also basically around the spheres, that would protect the spheres as well. And of course, you could make glass from all kinds of materials, and I think I have a video for that here. Just to make the point. So this guy has got an AK-47, and that's his boss there behind, and yeah, and that's bulletproof glass, as you can see. So you can make glass that's completely bulletproof, and you can make tempered glass. You can put impurities in like titanium. You can put metal wires in when the glass is molten, aluminium or iron metal fibers, and then when it's blown out, you've got stronger glass. So there's a lot of things you can do with the glass to make it stronger. You can put coatings on the glass as well, and the idea is you've got multiple glass spheres that act like a Whipple shield. And Marty's saying, I think that multiple shield picture was from Sierra Space for that inflatable station concept. Yeah. I think a lot of spacecraft have these Whipple shields. The Crew Dragon that had the dome had a Whipple shield as well, and that was made of glass. So yeah, this is something that we know how to do. Glass is well understood. It's been manufactured for thousands of years, and you can make all kinds of glass. I think one of the comments was about using borosilicate glass, which can withstand high temperatures. So you can dope the glass compounds with various other compounds and properties to make them stronger. And Ham Judo saying, the biggest risk in a habitat with a breathable air is fire. There has to be multiple stairs and elevators. Yes, I think I have one of your comments where you're saying about the fire safety issue, which is, yes, that's obviously a big issue. And I guess in the design, you'd have stairs on these decks, so you could take the stairs rather than the central elevator, which obviously everyone would be going to. But I think the habitat size is quite small. It's 10 to 20 people, but still you need stairs. So you could basically evacuate from any deck, any floor. You could get back to the base, get back down here to the, hopefully there's a tunnel and so on. So what else? Have I read this comment? Yes, so this comment, Marty is saying, I think it is only a concept video, but the rendition looks so precarious. I thought it was going to tip over and roll away. I think I'll say in my LabTubes. Thanks. Yes, I mean, I had the same thought when I saw it as well. It does look very precarious, and it doesn't look like the weight of the sphere with all the equipment could stay like that. It would just like topple over. But I quickly did this here. And this is just a thought, is that if you put it inside a crater and then backfill the crater with regolith, then you've got support from all the regolith. So you could either find a crater that already exists, that's the right size, or you could just excavate a bowl shape and blow the sphere from the base of the crater and then just backfill with regolith to provide support. So that's just an idea. I don't know if that would work. But yeah, so that's the first set of comments, but we have more comments. So, okay, yes, Ham Judo, who just said about the issue with the, in the case of a fire, says, no qualified fire marshal on Earth would approve a structure that large with only one exit. NASA is way more safety conscious than a terrestrial fire marshal. After a safety review, expect the design to include at least 2 sets of stairs that are widely separated. I expect the stairwells will act as emergency shelters with an independent emergency air supply. Elevators will be associated with each stairwell. This makes a much larger footprint. Think closer to dome than lollipop. Yeah, so obviously fire safety would be a very important issue. And yeah, I'm sure you have, you'd probably have maybe spare spacesuits and oxygen supplies throughout on each deck, just in case the worst happens and an impactor gets all the way through. Yes, but I think the inhabitant size would be quite small. It'd be, 10, 20 people to begin with, maybe. But yes, you need all the safety precautions. Yeah, and NASA would obviously be all over that. So Marty's saying, I worked in a glass factory and was impressed by how strong it was, but at the same time, so easy to shatter. Moon bubbles, though, would be different glass. Yeah, I think the technology for glass is very advanced on Earth. So you could dope it, and yeah, you'd use it as a Whipple shield, multiple concentric spheres, and you could have barriers, basically metal barriers at the side. And you could put it slightly inside in a crater and backfill with the regolith. So there's various things you could do, not 100% perfect, of course. I mean, if an impact hits straight from the top, it would be bad. But yeah, there's certain things you can do. So let's see, where was I here? So I've done Ham Judo's comment. So James Gibson is saying, interesting. I've always wondered if this was possible. My Pyrex glassware always impressed me, given that silicates are already on the moon. The Pyrex is made from borosilicate, so you need a lot of boron to make it. It's abundant on the moon, question mark. Well, not probably. You need to get some from Earth. So yes, borosilicate is used in Pyrex, and it can withstand high temperatures. So you probably have to dope the glass with that. Maybe just the outer shell or something. I don't know, the outer sphere. But there's impurities you can add to glass, depending on what property you want to give it. And James Gibson is saying, thanks for the prompt. Indeed, boron is present on the moon in very minor quantities, less than part per million, if I'm reading the reports correct. But either way, yes, rare, and probably needs to be bought from Earth. Yeah, you just bring a certain amount from Earth to dope the glass in its molten state. Make sure it's stirred in, and then when you blow it, it's got that, whatever that property is you want. And some more comments. Winkley is saying, I don't understand how glass is supposed to stand up to meteor impacts. Layers are no layers. I also don't understand how a large glass orb like that, actually layers of them, is stable atop the mobile kit module that blows it up. Even in low gravity, it looks like it would topple over. Despite all of this, the concept is intriguing and exciting. If it can actually be made to work reliably, this concept could be very useful in lava tubes and caves on Earth's moon and Mars. I'm confused about how it could be applied in open space. So yeah, we kind of gone over some of the ways around the issue. You could put it in a crater and then backfill with regolith. You've got multiple spheres for a Whipple shield, and yeah, you can change the properties of the glass. So there's ways you can make it more stable so it doesn't topple over and protect against impacts. And Tom Fraser saying rock meets windshield, which is the same kind of comment. And Wayne's World say interesting ideas, quite plausible. Wonder if it's sustainable. So there's a phase 2 study now. So hopefully we'll get more details and more simulations, and hopefully we get a tech demo they can actually send to the moon and try blowing up a glass sphere and see what happens. And Dave in Vegas, absolutely, let's do it. The technology has a lot of positive advantages and could work well when combined with other types of habitats. Yeah, like you've got the prefabricated habitats, the multi-purpose habitat, which will be part of the Artemis base camp. That's the usual way of doing things. We build the entire habitat on Earth, outfit it, and just send it to the moon, and there's your habitat. Then you've got inflatable habitats, where you've got a central core that's like metal or aluminium, and then you can inflate it to be much larger, to have a much larger volume. So Sierra Space is working those kind of inflatable habitats. And then you've got the just 3D printer habitat. Icon Technologies is working on large-scale 3D printing of habitats. And then you've got this idea of inflating a glass sphere. So let's have lots of different ideas of how to produce these habitats and try them out and see what works. And Alex Despland is 4939 is saying, just tens of meters isn't really useful for much. You need at least 100, if not thousands of square meters of space inside the bulb to be of use. Why is the small square footage of legally rentable space in most countries? Why is the small square footage of legally rentable space in most countries? And Ham Judo saying the diameter is 10 to 30 meters. For example, a 20 meter internal diameter means a useful radius 10 meters. So the central floor will have 314 square meters. The total volume would be 4,200 cubic meters. So yes, so the volume, I think, from algebra is like the cube of the radius. So 10 meters means you're talking about 1,000 cubic meters or some large number for cubic volume. So the volume is quite large. And as you can see from the graphic, I don't know if I've got the graphic still. Yeah, here it is. Bring up this graphic. There's a lot of space inside there. There's lots of decks and floors and bridges. It can support 10 to 20 people, a lot of working space, communal areas, living areas, and for food production. So it's quite large. Even at 20 meters, and of course at 50 meters, I don't know what the internal volume would be, but it would be huge. Yes. So, okay, that's the second one. And here's another sheet of comments. So Saint Rachel Gerard is saying, if they really want to take space exploration seriously, this is the kind of technology needed. Let's try it, right? Let's do a tech demo, put it on the moon, and see whether you can blow glass spheres and how big they can be. And another Glenn is saying, why do these components need to be able to Okay. So this is on a different video. This is another video. I saw people still leaving comments on it, so I decided I'd read some of the comments. So this is on Rendezvous Robotics. If you watch that video, this is about self-assembling tiles. You basically flat pack a load of tiles, and when they're released, they can self-assemble into large structures in space. So this is another way of building habitats. So that comment was about, yes, this is awesome. Another Glenn is saying, why do these components need to be able to self-assemble? It seems a lot of ask of aerospace components. These components need to be able to perform their primary function and also be able to self-assemble, ? Maybe it would be better to assign some assembly required spacecraft and spacecraft assembler separately. Maybe the spacecraft assembler needs assembly too. Once assembled, the spacecraft assembler assembles spacecraft. So what he's saying is basically just have the tiles flat packed, but manually put them together. So the idea is you don't want to do that for multiple reasons. First of all, you need people, and astronauts are very expensive, and you need they'd have to spend a lot of time assembling it. It would be very expensive. So you want self-assembly, and he's saying that it sounds really difficult, but this has already been demonstrated on the International Space Station. They're now on the 5th generation of these self-assembled tiles, so it definitely works in small scale. And next year they're going to launch 32 tiles, and they're dinner plate size tiles, and they're going to try and completely create an enclosure, a fully enclosed structure purely from self-assembly. And Marty is saying, I may not be a fan of the glass dome, but I'm always happy to be proven wrong. Same here. Even if I'm skeptical on something, I mean, hopefully it works. I'm happy to be proven wrong. So this other comment, this is from Charles Blythefield. This is a super interesting idea. Question: in order to self-assemble, I assume the tiles need a compute module, various sensors, and a propulsion system that allows movement and stopping in all 3 directions, which requires small thrusters, a source of energy, and a propellant. Therefore, the benefits of modularity and self-assembly come at the cost of the aggregate mass of all this and the cost to engineer these features into every tile. I'm thinking of trade-offs such as balancing this aggregate mass against, for example, mass in the form of a more robust locking system or the inclusion of piping or wiring to enable a network function. How does this benefit cost equation compare with another model with, say, similar tiles that can interlock as shown, but that require an external assembly robotic system which can attach tiles in the needed configuration and therefore do not need the hardware to move and self-assemble? So that's partially true. It does have a lot of compute, it does have a lot of sophisticated sensors and software, but it doesn't have a propulsion system. This is the key thing to understand. It doesn't need a propulsion system because instead it has permanent magnets around the tiles, around the edges of the tiles, and they can produce a lot of thrust. I think it's 100 newtons per tile, just because the magnets attract each other and pull the tiles together. So when the tiles are released, they're released into a bounded volume. There's some kind of net or enclosure. So they're not just free floating, they're enclosed, and you can guarantee just through the random motion in a bounded volume, the tiles will come close to each other. And when they do, with the sensors and so on, they can snap together where the magnets are and snap together and connect. And it also has some intelligence in the software and sensors that it can detect a bad connect where they don't connect properly, and it can send a pulse through the magnets which will cause them to fly apart. So it has sophisticated sensors, software, and compute, but no propulsion. So that's why it's so such an interesting concept, is that you can self-assemble very large structures in theory without needing propulsion, just compute and sensors and software. And like I said, it's on its 5th generation. It's flown to the ISS. It's flown on Blue Origin's New Shepard and 0G, and I think it's flying to the ISS next year with 32 tiles, which are larger and will self-assemble into fully enclosed habitat. That's the theory. So that's super exciting, and yeah, so there's a lot of exciting things happening in space, in the in-space assembly and manufacturing area, and a lot of exciting things happening on the lunar infrastructure. So in terms of what I'm doing next week, I'm not quite sure what I'm doing next week. I'm probably going to do a lunar infrastructure one. There's more I want to talk about. I want to do more on lunar lava tubes. I've had a video idea for that for a couple of weeks. I've been doing other things in between, but maybe I'll get around to the lunar lava tubes video and something else. So anyway, thank you for joining, and I'll see you next week at the same time.